you need to find a file in your file system, a word in your document, or a variable name in your code. Computers need to do many more things internally, like finding a place in memory where they can store your data, finding the address of a specific hardware device, and so on. It's interesting that not all search problems are identical. Some are harder than others. For example, long ago, there were these things called phone books. They stored people's names and phone numbers, and they were sorted by the first letter of the person's last name. Searching through a phone book isn't hard. In fact, it's incredibly quick, as you can use the binary search algorithm to do it. You open the phone book at some random position and check if the last name where you happen to be begins with the letter that is before or after the letter you're looking for. You then open at a random position about halfway through the remainder of the stack in the right direction. Repeating this will get you to the right place in about logarithmic time. So if you have n names in the phone book, and maybe n is 10,000, then you expect to find the number you're looking for in log of 10,000, which is about 4 attempts. Not bad. Searching through the phone book is quick because it has structure. The names are sorted, and we can exploit that if we want to be quick. But not all problems are that easy. When we say we're trying to find a needle in a haystack, what we really mean is that we are dealing with something that has no structure at all. The time needed to solve this type of problem is linear in the size of the haystack. The best thing we can do is to simply check each item in the collection and see if that's the one we're looking for. How could it be any quicker? The Grover algorithm is an example of how extending the model of computation by allowing the information to be quantum allows for an algorithm that has a chance for being faster than any classical option. Instead of a runtime proportional to the number of items in the collection, the Grover runtime is proportional to the square root of that number. We call this a quadratic speedup. There are tons of resources, including in our very own Classiq documentation, where the principle of operation of the Grover algorithm is explained in depth. It's not really possible to do it justice in a quick video. Instead, we will look at how we find solutions to a simple arithmetic expression with Grover and get a feel of how it works and what the circuit we synthesize using the Classiq platform looks like. Searching for the solution for a single arithmetic expression is a simple problem. It's so simple that you may be wondering what it can teach us about quantum computation at all. The reason to do it is that it's very easy to get intuition about the results. We can look at what we get and immediately see if it's correct. In addition, there are computationally difficult problems where solving many arithmetic expressions together is required. Those type of problems can also benefit for quantum computers. So we begin with a simple arithmetic expression. Let's find all the possible solutions of the expression a plus b is equal to 1. Let's see how to run the Grover algorithm on this expression in the Classiq IDE. We first define an oracle function. The oracle is a function that flips the phase of the state for states that are compatible with our original expression, but doesn't flip the phase of states that do not. In the IDE, we define the oracle here. We set the size of each variable in the expression here. The size is the number of qubits we allocate to encode the number, just like having to allocate some bit number to encode a number on a classical computer. The oracle has the effect of tagging correct quantum states for the next stage of the algorithm, called amplitude amplification. The effect, as the name suggests, is to amplify the amplitude of tagged states while suppressing others. This step can be repeated several times to sufficiently amplify the correct state's amplitudes. We can specify the number of times we want to repeat the amplification stage here. Selecting the correct number is not trivial, and you can find more information on how to do this in the Classiq documentation. We now synthesize the circuit by clicking on the synthesis button and see the circuit we get. There are two blocks we can expand, look at the repeat block, and see it is indeed repeated the number of times we specified. Finally, let's execute the circuit on a simulator. Let's simulate on the IBM Air simulator. I'll set the execution details. We'll simulate the circuit about 2,000 times in this case, and get the resulting count histogram. We see that the A register has equal probability to be 0 and 1, and similarly, the B register has equal probability to be 0 or 1. So, indeed, we get the unspectacular result that 0 plus 1, or 1 plus 0, indeed equal 1. We've successfully synthesized and run the Grover algorithm on a quantum simulator. I hope you enjoyed this session. This is just the first step, and it already results in a non-trivial circuit, which would be hard to design manually. Things only get more complex from here, showing why automated design is so great. Thank you.